Ladies and gentlemen, my name is Mykhailo Fryz. I'm Associate Professor of Computer Science Department at Ternopil Ivan Poluy National Technical University. And I'm very glad to represent the result of our research titled as Characteristic Function of Conditional Linear Random Process. First of all, let me talk about practical motivation of our research. There are a lot of signals that can be modeled like a sum of large amount of stochastic impulses occurring at random moments of time. The linear random process with infinitely divisible distribution can be often suitable mathematical model for such kind of signals. This model is representation of additive interaction of infinity number of stochastically independent random impulses occurring at the jump points of Poisson counting process. However, if these impulses are stochastically dependent random functions or occur at non-Poisson times, then adequate mathematical model is conditional linear random process. We have this situation in the problems of the electricity consumption forecasting, analysis of radar clutter, dynamic loads of mechanical systems, electrophysiological signals of the brain, etc. The idea of a conditional linear random process definition is to generalize a linear random process by replacing the deterministic kernel with the random function, which obviously has to satisfy the certain conditions to ensure the convergence of the corresponding stochastic integral and has the properties that allow the practical application of such kind of model. Very often a linear random process is also interpreted as the output signal of some linear dynamic system where the input signal is the white noise. From this point of view, the idea of constructing a conditional linear random process is to represent it as the response of the linear dynamic system with random parameters to the input signal in the form of white noise. The problem of our paper is to justify the expressions for characteristic functions of the process and also find the conditions to be strict sense stationary. So let me represent the results of our research. On this slide, the univariate characteristic function is represented. This expression has been obtained using the conditional characteristic function approach. On the following slide, the m-dimensional characteristic function of conditional linear random process has been represented. We can conclude in particular that probability distribution of the process belongs to the class of mixture of infinitely divisible distributions. The obtained expressions can be used for probability analysis of the mathematical models of stochastic signals in different applications of computer science and information technologies. For example, the mathematical expectation and moment of second order are represented on the slide. The expressions have been obtained from the above characteristic functions. Also, covariance function and the moment functions of higher order can be obtained, and you can see the results in our paper. Finally, the sufficient conditions for conditional linear random process to be strict sense stationary have been obtained in our paper. That conditions are, first of all, the random kernels phi of tau t and the shifted version phi of tau plus s T plus S have to be stochastically equivalent in the wide sense. That is, their finite dimensional functions should be equal. And the second condition, that the process with independent increments should be Levy process. The Venn diagram representing the relationships between the classes of stationary random processes we considered in our paper is represented on this slide. So we can see that linear random process is the subset of the class of conditional linear random process, and also set E represents the process of the same structure but driven by renewal reward process. But we didn't consider this kind of process in our paper. The conclusions are represented on the current slide. Thank you for your attention. I would be glad to answer your questions. Thank you very much.